Now let's look at the rules that must stay true after every operation. We call these the invariants. The first one is telling a full queue from an empty one. Now look at the tricky case. When you enqueue and deque many times, front and rear move around the ring. They can end up on the same index, and that one index cannot tell you if the queue is empty or full. There are two clean ways to fix this. The first way is an explicit count. You keep a separate counter of the live elements. The queue is empty when count is equal to 0. It is full when count is equal to capacity. The second way is to keep one slot empty. You never fill the last free seat. Then full means rear plus 1, mod capacity, is equal to front. The cost is that you can only store capacity minus 1 elements. Watch out for this trap. You may think front is equal to rear always means empty, but once the ring fills up, front and rear meet again at the same seat when it is full. The two indices alone cannot tell the cases apart. A count, or one reserved empty seat, gives you the answer. This chapter uses the explicit count. It is the easier rule to read and to teach. Both ways are correct. What matters is that you pick one and state it clearly. An invariant is a rule that stays true after every operation. Let's list the rules the circular array Q must always keep. Every correct enqueue and deque restores all of them. First rule. The count stays between 0 and capacity. In other words, 0 is less than or equal to count, and count is less than or equal to capacity. The queue can never hold more elements than the buffer size. Second rule. Front and rear always stay inside the range 0 to capacity minus 1. Every index update is taken mod capacity. We never leave an index as a raw, out-of-range number. Third rule, and the important one. Front is equal to rear can mean empty or full. The count tells you which. This is the rule that every bug in this chapter breaks. The linked queue has its own rules. It uses nodes and pointers instead of one array. Let's read the 3 rules it must always keep. First rule. When the queue is not empty, rear arrow next is equal to null. The tail node is always the last node. Nothing dangles past it. Second rule. Front is equal to null exactly when the queue is empty. This is the one check that guards every deque. Third rule. When you empty the queue, you must reset both front and rear to null. If you forget rear, it keeps pointing at a node you already freed. That is a dangling pointer, and it is a common bug. Let's check the central idea. With the explicit count approach, what does front is equal to rear tell you on its own? And what extra fact clears it up? Think about it before the answer appears. Now the answer. On its own, front is equal to rear only tells you the queue holds either 0 or capacity elements. It cannot pick between them. Count is equal to 0 means empty. Count is equal to capacity means full.